you are dealing with a gas consisting of a mixture of A and B molecules. Equimolar counter-diffusion means that the rate of diffusion of A to the right is the same as the rate of diffusion of B towards the left. Towards the left is in the negative direction. The concentration of gas A plus the concentration of gas B is equal to the total concentration. You can differentiate both sides of this equation with respect to y, the distance towards the right. The concentrations of A and B vary, but the total concentration stays constant, and the differential of a constant is 0. After the differentiation, you can see that the slope of A and the slope of B are equal with respect to distance y, but with the concentration of A decreasing, and the concentration of B increasing, as you move along y. In the following equation, note that the equation for NB is multiplied by -1, left, and right. Substituting for dCB by dy from above. Substituting for N, A, from above. And if you also substituting for negative NB, from above. From the equation at the bottom, you can see that the diffusivity of gas A through gas B is the same as the diffusivity of gas B through gas A for equimolar countercurrent diffusion. You can integrate Fick's law like Fourier's law for a stationary gas, and for steady-state conditions with a constant rate of diffusion, N, A. The diffusivity is constant too. In this slide, you have diffusion happening in a gas that is also moving in the same direction as the diffusion, y. Na dot is the molar flow rate in moles per second. Q is the flow rate in cubic meters per second, and this is equal to the cross-sectional area, AX, times the velocity, U. The molar flow rate, divided by the cross-sectional area, is equal to the molar flux, N, A. This molar flux is the result of the bulk flow only, and this is given by U. Because the gradient of the concentration of A is negative, as you can see in the diagram, both terms are positive and serve to increase the total transfer, given by n, A, dashed. The integration was performed by the lecturer, so you may be able to simplify it further. You should also check it for accuracy. Say you have a surface on the right-hand side that absorbs A only. B will therefore be stationary. The concentration of A, C, A, at the surface could be zero due to its being absorbed at the surface. This means that the concentration of B will be high at the surface, decreasing as you move away from the surface towards the left. As A molecules move to the right, and B molecules are stationary, there is a bulk movement of molecules towards the right. Due to the concentration gradient, B molecules will diffuse to the left. However, there is a bulk flow to the right, as A molecules are removed from the gas at the surface. As there is no net movement of B, the diffusion of B will be balanced by the bulk flow of B in the opposite direction. d, c, b, over, d, y, is equal to minus d, c, a, over, d, y, as shown in slide TPRCH9-1. This is a c, a, plus c, b, is equal to the constant total concentration of the gases. You need to check that the diffusivities of A and B are equal for stationary B as well. This equation can be used to calculate the diffusion rate, over a known distance, and concentration difference. In certain circumstances, C, A, 2, will be 0 if point 2 is at the surface, and all available A, at the surface, is absorbed by the surface.